Hello everyone. Today we will learn the concentration terms of solution, or how do we measure the concentration of the given solution. So first of all, what do you mean by the solution? Solution, it consists of the two parts, or it consists of two components. One component which is present in lesser amount or in minimum amount is known as solute, and other component which is present in maximum amount or in higher amount is known as the solvent. A solution consists of two components. One is solute, other is solvent. So, how do we define solution? Solution is a homogeneous mixture of solute and solvent. It is a homogeneous mixture of solute and solvent. When we mix these two components, we get the third new component, that is solution. Now, in this lecture, we will learn how do we measure the concentration of a given solution. So, the first unit to measure its concentration is strength. How do we define the strength of a given solution? Strength of a given solution is measured in grams per liter, and it is defined as amount of solute present in 1 liter of the solution. Strength of a given solution is amount of solute in grams that is present in 1 liter of solution, and mathematically it is calculated as mass of solute. Basically, this solute is measured in grams divided by volume of solution, and this solution should be measured in liters. So, SI unit of the strength is gram per liter. So, the first unit to measure the concentration of the solution is strength, and strength is defined as the amount of solute present in 1 liter of the solution, and its SI unit is gram per liter. Next unit to measure concentration is mass percentage. Next unit to measure the concentration of the solution is mass percentage. Percentage means in 100 parts of solution. The word percentage represent 100 parts. Therefore, we define the mass percentage of a solution is mass of a given solution, or mass of a component that should be present in 100 parts of the solution. For example, if we said a sugar solution has its concentration 10%. The concentration of a sugar solution is 10%, means 10 gram of sugar is present in 100 gram of solution. 10 grams of sugar is present in 100 grams of solution. Therefore, mass percentage of a given component can be calculated as mass of that component divided by total mass of the solution and multiplied by 100. This mass percentage does not have any unit. Why it has not unit? Because mass of the component as well as total mass of the solution, they have same unit. One is on the numerator, other is denominator. They both are cancelled out. Therefore, the mass percentage has no unit and it is a unitless quantity. It is represented only the number. Next unit to measure the concentration of the solution is ppm, or it is also known as parts per million. The full form of ppm is parts per million. This unit of concentration is used where the amount of the solute is very less. For example, in medicines. How do we define ppm? Just like percentage. Percentage means the weight of the substance or the mass of the substance present in 100 parts. Similarly, ppm means the mass of the solute or the mass of the component that should be present in 1 million of the solution. 1 million means 10 raised to power 6. Therefore, we define ppm as the mass of the solute or the mass of the component that should be present in that should present in 1 million of the solution. And mathematically, ppm can be calculated as mass of the component divided by total mass of the solution multiplied by 1 million, that is 10 raised to power 6, and its unit is ppm. ppm, just like percentage, can be represented as this sign. Similarly, ppm is represented as this. Now see the one question related to this concept or this unit, that is ppm, and the question is 1 liter of sea water has mass 1 liter of sea water has mass 1050 grams and it contains 6 into 10 raised to power minus 3 gram of dissolved oxygen. question is 1 liter of seawater has mass 1050 grams. It contains 6 into 10 raised to power minus 3 gram of dissolved oxygen. Calculate the concentration of oxygen in ppm. You have to calculate the concentration of oxygen in terms of ppm. How do we solve this question? In this question, the mass of the solute is 6 into 10 raised to power minus 3, which is oxygen, and the mass of the water or the mass of the solution is 1050 gram. So, the concentration of oxygen is mass of solute. Here solute is oxygen, so mass of oxygen divided by total mass multiplied by 1 million, that is 10 raised to power 6. Here mass of oxygen is given to you, that is 6 into 10 raised to power minus 3. The total mass of the solution is also given to you, that is 1050, and multiply these terms by 10 raised to power 6. When you solve this, you get 6 into 10 raised to power minus 3 plus 6, as base is same, so power should be added, and it comes out to be 6000 upon 1050. When you solve this, you get answer 5.7 ppm. Hence, the concentration of dissolved oxygen in sea water is 5.7 ppm. Now, the next unit to measure the concentration is mole fraction. The most important unit to measure the concentration, or the new unit, is mole fraction. Mole fraction is a new term and it is represented by the letter X. How do we define the mole fraction of a component? As we know that the mole or moles of different components are represented by the letter N. So the mole fraction of a given component is defined as the number of moles of that component that should be present in total number of the moles in a given compound. Mole fraction of a given component can be calculated as mole fraction is equal to number of mole of that component divided by total number of moles. Hence, if there are two components in a given solution, that are the component 1 and component 2, let us suppose that for component 1 the number of moles are N1, for component 2 number of moles are N2. So the mole fraction of component 1 is X1 and mole fraction of component 2 is X2 and can be calculated as N2 divided by N1 plus N2. And one more important thing, if we add different mole fractions in a given solution, then the sum is always equal to 1. If in a solution two components are present, then the sum of two mole fractions is 1 if it contains n component. If a given solution contains n component, then the mole fraction of all components, the sum of all component of mole fraction should be equal to 1. If it contains two components, then the mole fraction of two components should be 1. If it contains 3, then x1 plus x2 plus x3 equal to 1. If a solution contains n components, then the sum of all mole fractions or n mole fractions should be equal to 1. And this mole fraction also unitless quantity. Why it is unitless quantity? Because numerator and denominator both have the same unit, that is number of mole. The number of moles on the numerator as well as denominator, they are cancelled out and it becomes a unitless quantity. Let us do one question related to the mole fraction. See the example related to the mole fraction. A solution contains two components. A solution contains two components, that is benzene and carbon tetrachloride, in which 30% of benzene is present, in which 30% of benzene is present, and you have to calculate the mole fraction of benzene. You have to calculate the mole fraction of benzene. How do we solve this question? For mole fraction, we know the chemical formula or the mathematical derivation. For mole fraction, we need number of moles of the different components. In this statement, two components are present. One is benzene and other is carbon tetrachloride. Here 30% of benzene. 30% of benzene means in this solution 30 parts of benzene and 70 parts of carbon tetrachloride are mixed together to form a solution. Here 30% of benzene and 70% of carbon tetrachloride, when they mix together, they form a solution. And in this solution, we have to find the mole fraction of benzene only. So first of all, we have to find the number of moles of benzene as well as number of moles of the carbon tetrachloride. How do we find the number of moles? For number of moles, we know that when you divide the mass of the solute or the given mass divided by its molecular mass, we find the number of the moles of that component. So first of all, we have to find the number of moles of benzene. For this, number of moles of benzene, mass of benzene, that is given to you 30, and its molecular mass, that is 12 into 6 plus 6, that is 30 upon 78. When you solve this, you get the mole of benzene. Similarly, we have to find the number of moles of carbon tetrachloride, that is mass of the carbon tetrachloride in the solution divided by its molecular mass. Molecular mass of carbon tetrachloride is 12 plus 35.5 into 4. Here 35.5 is the atomic mass of 1 chlorine and 4 are the number of the chlorine atoms. For the number of moles of carbon tetrachloride, 70 is the mass of the carbon tetrachloride and divided by its molecular mass. For molecular mass, 12 plus 35.5, 35.5 is the mass of the chlorine multiplied by 4. When you solve this, you get 70 divided by its molecular mass, that is 154. Solve this, you get the relative number of moles of the component, and the relative number of moles of benzene is 0.3 approximate or 3.8, and number of moles of carbon tetrachlorides in this question is 0.49. Now these are the different number of moles of carbon tetrachloride and benzene, and we have to find the mole fraction of benzene. For mole fraction of benzene, we have the formula. Mole fraction is represented by X, as we have to find the mole fraction of benzene. So I write here the molecular formula of benzene, that is C6H6, and it is equal to number of moles of benzene divided by total numbers of moles, that is number of moles of benzene plus number of moles of carbon tetrachloride, and it is equal to 0.38 divided by 0.38 plus 0.49. When you solve this, you get the mole fraction of benzene, and in this the mole fraction of benzene is 0.4, or approximate it comes out to be 0.5. This is the mole fraction of benzene, which is present in a solution of carbon tetrachloride and benzene, in which the amount of benzene is 30%. This is all about the mole fraction.